Hey guys, welcome back to another new week. Today we're going to be finishing off the last lesson of our solutions unit, unit 11, with something a little different that's called LeChatelier's principle. And this is going to kind of take a look at reactions that occur in the solution state. And specifically, we're going to be talking about reactions that are reversible, which means they go both ways. So you can take the reactants and convert them into products, but then you can take those products and reconvert them into reactants. And those forward and reverse processes are occurring at the same time. And so we normally play this really fun game, where different people are either reactant formers or product breakers, and it's kind of like a little competition. But to help out with that idea of what a reversible reaction actually is, I'd like to show you a little simulation first. And so what I'm going to do is I'm going to add in some reactants, which are molecules A, these little green guys here. And so I'm going to go ahead and add just several more of those. And so you'll see A getting bigger because there are lots of them. Now, what they're going to do is in the reaction, they're going to be converted from these green molecules into the red molecules. And so what I'll do is I'll lower this activation energy, and that will allow the reaction to proceed much more quickly. But now here's the part that I'd like you to notice about the term reversible. You'll notice that a lot of the green molecules are moving to the right to be converted into the red product molecules. However, if you'll watch closely, you'll notice that the red molecules can also bounce back to the left and be reconverted into reactants. Now, if I add some heat, these processes are both going to speed up. We're going to have the green being converted to the red and the red being converted to the green, so on and so forth. Now, what's also interesting about reversible reactions is that they can favor either the reactant or the product side. So at the moment, currently, the reactants are being transitioned into products at about the same rate. And so you'll notice, here, let me pause this. Do you see how the size of the A and the B are about the same? And that means we're converting the reactants to products at the same rate that we're reconverting the products to the reactants. And that's a state that's called equilibrium. Now, what we can do is we can adjust the reaction so that it favors one side over the other instead of being at equilibrium. So for example, watch what happens as I add in more of the product. You're going to notice now that this A is a lot... Oops, I didn't give it enough time. That the A, when I started out, was a lot larger than the B. So now you can see it's larger, but if I just let the reaction run, you can see how they're going to try to start evening back out again. So the reactions like to try to arrive at equilibrium. All right, so now let's go ahead and go back and try to put LeChatelier's principle in context of this idea of reversible reactions and this idea of equilibrium. So LeChatelier's principle talks about what happens when we apply some type of stress to a chemical reaction system that's at equilibrium. And it's interesting that just like us, when we're stressed, we tend to want to undo it or get out of it. Chemical reactions tend to behave the same way. And so what LeChatelier's principle allows us to do is predict how the reaction will react to certain stresses that we apply. But first, anytime that we're going to apply this principle, it's important that our system is starting at equilibrium. And like we talked about in the simulation, what that means is that the rate of the forward reaction is going to be equal to the rate of the reverse chemical reaction. So you'll be making the products in the forward reaction at the same rate that you are remaking the reactants in the reverse reaction. And so just to make sure we're good on our terminology, so when you're going from reactants to products, that's what we're calling the forward reaction. When you're returning from products to products to reactants, that's called the reverse reaction. So that's what we mean there. And so what LeChatelier's principle says is that if a stress is applied to a system at equilibrium, then the system will shift, if possible, to remove the stress. Okay, and so kind of like, us as students and teachers for school, if we're kind of stressed by school, that often helps us maybe long for summer, a little bit more, which is right around the corner. And so reactions are the same way. Whatever stress is applied, they try to do the opposite and shift to reduce the stress. And so we're going to take a look at a few different factors that can be used to create a stress within a reaction system. One of those things is concentration. And simply what that's going to mean is the amount of products or reactants. So the amount of reactants/products. And this is something that you guys watched me manipulate on the simulation by adding in more of those little green molecules. And so here's the deal. If we add in more reactants to stress a reaction out, it's going to shift toward the opposite side, toward the products. It's going to rapidly use up those reactants to get all that extra out of the way, and so it will start making the products as a result. Now, the opposite is true if we add more products. So if we add more products, the reaction is going to shift the opposite direction toward the reactants. So the rule is do the opposite of whatever stress is occurring. So we've got an example here that says which way will the equilibrium shift if we add more hydrogen to this reaction at equilibrium. So what happens is we're going to be adding more of hydrogen, which is on the reactant side. So if we have increased the concentration of the reactants, we need to shift the opposite direction toward the products. So the way we'll word this is we'll say it will shift toward the products. And again, the products are located on the right side of our chemical equation. Now, it gives us another scenario here where instead of adding hydrogen, what it wants us to do is remove some of the product NH3. Now, what we're doing is taking away from the product side. So the thought is, if you take something away from the right, the opposite of taking away is replacing it. So if we've taken away some of the product, we need to shift to the product side to remake it. So if you add something, you go to the opposite side. If you take away something, you go to the same side. So in this example, we'll also be shifting toward the products, which is going to the right. All right, so that's how adding or taking away our products or reactants affects the shift in the chemical reaction. Now, another way we can change things is by affecting temperature. And so sometimes our reactions are designed so that they release heat. This is what's called an exothermic reaction. And so these reactions are typically written with heat treated as a product on the right side of the equation. A reaction that requires heat to be put in is called endothermic. And heat, in that case, will be treated as a reactant on the left side. And so what that does is it makes it really easy for us to apply the same rules that we talked about with concentration. So our example 2a, it says which way will the equilibrium shift if the system temperature goes up, which means that heat is being added. So here, heat is on our product side, which means that this reaction is exothermic. So if I'm adding something to the right side, I need to shift to the opposite side to use up that extra heat. So again, if you're adding, you go to the opposite side to use up the extra. So in this case, we'll be shifting toward the reactants, which are on the left side of our equation. Now, it says using the same reaction, make a prediction which way the reaction will shift if heat is removed. So heat's still on our product side, but this time we're taking it away. So if we are losing heat, we need to shift back to that same side in order to replace it. So in this case, we'll be shifting right toward the products. So again, if you add something, shift to the opposite side to use it. If you take away something, shift back to that same side from which it was taken so you can replace it. All right, so our next way we can stress a reaction is by changes in pressure. Now this affects substances that are in the gaseous state. So essentially that just means that they're gases, and you'll be looking for that little symbol with a G. Now again, gases, because they tend to be fast-moving particles that are small, they can occupy whatever space their container gives them. But if you apply more pressure, that gives them kind of less space to move around. All right, so it says when the pressure is increased, the reaction is going to shift toward the side with the fewest number of moles of gas. And so what will happen is the less gas you have, the better able it will be to accommodate a higher pressure. And so what this means on the flip side, if pressure is decreased, you'll want to shift to the side with more gas in order to try to maintain that pressure that was lost. So if pressure is decreased, shift toward side with more gas. All right, so our next example, example 3, says which way would the equilibrium shift if the pressure is increased? And what we're going to assume is that all of these molecules are in the gas phase, which they are. And so the way we figure out how much gas we have is by counting the number of moles from the coefficients. So on this left side, we have a total of 1 plus 3, which is 4 moles of gas. On the right side, we have 2 moles of gas. So the reactant side has more, and the product side has less. So they tell us which way, or they ask us rather, which way will the equilibrium shift if the pressure is increased. So if the pressure is increased, our reaction is going to shift toward the side that gives us less gas. So in this case, the side with less gas molecules will be the product side on the right. Now, if they had asked us which way would we shift if we had less pressure, we would shift toward the reactant side because it had more gas. All right, so almost finished here. We're going to look at our fourth factor. Now, the nice thing about this factor, a catalyst, is it does not actually cause a shift in the reaction. All it does is just speed up the rate at which both the forward and reverse reaction occur. So it makes you make the reactants faster, but it also helps you make the products faster and also remake the reactants at a faster rate as well. So it does not create a shift in equilibrium. It speeds up both sides of the reaction equally. So in our example here, it says the system below is already at equilibrium when a catalyst is added. What happens to the position of the equilibrium? Does it shift right, left, or no change? So here, there's no change in equilibrium because the only thing that's happening is the reaction is speeding up. So it's a nice thing about catalyst. All right, so what we've got for you kind of right quick is some practice problems to kind of apply what you've learned. And so I'm going to walk through a couple of them with you. And then for the other ones, you'll kind of finish them on your own. And here are some answers at the bottom for you to check. And when you're checking your answers, before I forget to say this later, the R stands for shifting right to the products. The L stands for shifting left to the reactants. And the NC stands for no change. All right, so let's take a look at this reaction right quick. So this one says, what would happen if we remove NH3 gas? So we're losing one of our products, so we need to replace it. So that means we would need to shift right toward the products. The second thing it asks us to consider is what would happen if we decreased pressure. So this is going to be affecting or be determined by how much gas is on each side. So on the left side, we have 4 moles of gas. On the right side, we just have 2 moles of gas. So a decrease in pressure is going to favor the side with more gas. So this means we'll shift left toward the reactants. All right, the next one is a factor on concentration. What if we add in more nitrogen on the reactant side? If we've added something, we need to take it away by shifting to the opposite side, which in this case would be right. Now, if we look at D, which says increased temperature, that's as if we were adding more heat. If we're adding something, we go to the opposite side to take it away. So we'll shift to the left. While we're at it, let's go ahead and do number 2 together right quick. And so in this one, we have an increase in hydrogen concentration. So we've added more hydrogen on the left, so we'll need to shift to the opposite side on the right. Then we have another example of increasing in pressure. So let's count our gas molecules. On the left here, we have 2 moles of gas, 1 mole of hydrogen plus 1 mole of chlorine. And on the right, we also have 2 moles of gas. So what this means is that if both sides are equal in the amount of gas, increasing the pressure will not shift left or right. There will just be no change because both sides will be affected by pressure in the same way. Okay. So now what you can do right quick is if you'll pause the video and finish trying these last 4 practice problems right quick, check your answers down here, and then if you'll come back to the video in just a second, I'd like to show you a video of a demo that we normally do with this to kind of help get you ready for the lab, and it's really cool because it involves lots of color changes. So if you'll pop back on, then we'll get to see that together. All right, so welcome back. Here is the Chatelier's principal lab video, and I'll leave the link in the description if you want to watch the entire thing. And so what this reaction is it's actually a color changing reaction where the reactant side is going to be pink and the product side is going to be blue. And so the way we're going to be able to detect which way the reaction is shifting is based on what colors we see. If it favors the product side, the mixture will turn blue. If it favors the reactant side, the mixture is going to turn pink. Okay, and it's reversible, so it can go either direction. So I'm going to try to kind of speed through different parts of the video so it won't take quite as long. And so what we're showing you kind of here is an example of what the colors will look like. So that light pink is the reactant side, the dark blue is the product side, and the purple is kind of the in-between, which is representing where the reaction is at an exact equilibrium in the middle, where you have equal amounts of reactants and products. All right, so let's go ahead and start with our test. So the first thing that we're going to do is kind of take one of our test tubes, and we're going to add some hydrochloric acid. Now, hydrochloric acid has chlorine in it, so that means that we'll be increasing the concentration of one of our reactants, this chlorine right here. Now, because we've added extra reactants, the reaction will have a tendency to shift toward the product side. So we should start to see a change that reflects a blue color, and we do. So now, what we're going to do is we're going to take another test tube. It's going to start out pink, but this time we're going to add calcium chloride, which is an ionic compound also containing chlorine. So again, the main change is going to be the addition of chlorine to the reactant side. And so if we had to make a prediction, we're going to predict that it should shift blue to use up that extra reactant. And so you'll want to look right at the bottom of the test tube where the calcium chloride goes in, and that's where you'll be able to see that shift to the blue product side. All right, now what we're going to do is take test tube 1, there you can see it a little closely, And so now we're going to take test tube 1 and add in some water. Now water in this case is on the product side. And so if we're increasing the product, it should reshift toward the reactants. So we should expect to see this test tube change from blue back to its original pink. And so we'll pour in some water here and wait and see what happens. All right, and there we go. Shifts back to the left pink. All right, so one more kind of chemical test on this. So what we'll do is take another plain pink test tube. We're going to add some hydrochloric acid to turn it back to blue. Then what we're going to do is add in some silver chloride. And so what this is going to do is it will precipitate some of the chlorine ions. So it's going to, or silver nitrate, I'm sorry. So what it will do is remove some of the chlorine ions. So if we take away the reactant chlorine, our reaction should shift back to the left to replace it. And so what we'll see is that this reaction is going to start turning a lighter pink as it tries to replace the chlorine that's being removed by the silver nitrate that he's dropping in. And you can especially see this kind of at the bottom there where it's starting to turn pink. Okay, so last two things we're going to show you are what happens with the heat factor. And so the first thing we're going to do is put this guy in a hot water bath and kind of heat it up and see what effect that has on the reaction. So here's our warm water bath. It's going to be at about, I think 76 degrees Celsius. It's got an infrared thermometer here, so this is kind of cool. So room temp for him there is about 25.5 degrees Celsius. And then what we see in the water is about 76 degrees Celsius, so that's definitely warmer. And so he's going to take that test tube and place it in the warm water. And what we'll start to notice is that the color, kind of if you'll look at the top there, is starting to shift toward blue. And so let's think about this and see if we can predict whether the reaction is exothermic or endothermic. So what we see is that the addition of heat makes the reaction shift toward the product side. And we know anytime we add something, we're shifting to the opposite side. So if we're shifting to the right, that must mean that the heat is on the left. So this must be an endothermic reaction where heat is treated as a reactant. And so what we can do to confirm that is we can take our test tube and we can place it in cold water, kind of an ice water bath. And by doing that, we're removing heat. And so if heat is on the left, if we take it away, we'll shift back to the left to replace it. And so we'll take out our cold water bath here. Just wait till they get it out. There it is. And so again, he'll kind of show us the temperature to, verify that this is indeed, colder. So this is about 9.5 degrees Celsius, so definitely a good bit colder. And so when we place that blue test tube in, we're removing some of the heat. And so we'll start to see it kind of from the bottom there, start to shift back pink to try to replenish the heat that was lost. All right, so anyways, that just kind of gives you a little preview into the demo we would have done in the lab that we would have gotten to do as well. But hopefully that helps give you a little visual to go along with LeChatelier's principle. But thanks so much for watching, and good luck on finishing the assignment.